Lesson: Architecture and Layers, Designing Neural Network Structures. Designing neural network structures involves understanding the intricate architecture and layers that form the core of deep learning models. Neural networks, drawing inspiration from biological neural systems, consist of interconnected nodes or neurons that process and transform data. The architecture of a neural network dictates how these neurons are organized and interconnected, profoundly influencing the network's ability to learn, generalize, and perform complex tasks. Professionals aiming to specialize in AI workflows and automation must grasp the intricacies of neural network design, leveraging practical tools and frameworks to build effective models. At the heart of neural network architecture is the concept of layers. Layers are sequences of neurons arranged in a specific order, each performing distinct functions. The primary types of layers include input, hidden, and output layers. The input layer receives raw data, while hidden layers perform feature extraction and transformation through nonlinear activations. The final predictions are made in the output layer. The choice and number of hidden layers, along with the number of neurons in each, can significantly impact the network's capacity to model complex relationships within data. One of the foundational architectures is the feed-forward neural network, where data moves unidirectionally from input to output. Despite its simplicity, the architecture's effectiveness is evident in applications such as image and speech recognition. However, more advanced tasks necessitate deeper networks, leading to the development of deep neural networks. These networks consist of multiple hidden layers, allowing them to learn hierarchical representations of data. The depth of a network correlates with its ability to capture intricate patterns, but it also introduces challenges such as vanishing gradients, which can impede learning. To mitigate such issues, specialized architectures like convolutional neural networks and recurrent neural networks have been developed. CNNs, characterized by convolutional and pooling layers, excel in processing spatial data like images. Their architecture efficiently captures spatial hierarchies by applying convolutional filters, which detect local patterns such as edges and textures. Pooling layers then downsample the feature maps, reducing dimensionality and computational load while preserving essential features. CNNs have revolutionized computer vision, achieving remarkable accuracy in tasks like object detection and image classification. RNNs, on the other hand, are designed to handle sequential data by incorporating recurrent connections that allow information to persist across time steps. This architecture is particularly beneficial for tasks like language modeling and time series prediction, where context and temporal dependencies are crucial. However, traditional RNNs suffer from vanishing and exploding gradient problems. Long short-term memory networks and gated recurrent units address these issues by introducing gating mechanisms that regulate information flow, enabling them to capture long-range dependencies more effectively. Frameworks like TensorFlow and PyTorch have significantly democratized neural network design, providing robust tools and libraries for building, training, and deploying models. TensorFlow, developed by Google, offers a comprehensive ecosystem with high-level APIs like Keras that simplify model creation. Its flexible architecture supports both CPUs and GPUs, making it ideal for large-scale deployments. PyTorch, favored for its dynamic computation graph, allows on-the-fly modifications, appealing to researchers and practitioners who prioritize flexibility and ease of debugging. Both frameworks support automatic differentiation, a crucial feature for optimizing neural networks through backpropagation. The process of designing a neural network involves several critical steps, beginning with data preprocessing. Data must be cleaned, normalized, and transformed to ensure it is suitable for training. This step often includes techniques such as data augmentation, which artificially increases the diversity of training data by applying transformations like rotation and scaling. Effective data preprocessing can enhance a model's generalization capabilities and robustness. Once data is prepared, the architecture is defined by selecting the appropriate type and number of layers. The complexity of the problem dictates the depth and breadth of the network. For instance, simpler tasks may require only a few hidden layers, whereas complex problems like image recognition might benefit from deep architectures with numerous layers. It is essential to balance model complexity with the risk of overfitting, where the network learns noise in the training data instead of underlying patterns. Techniques like dropout, which randomly deactivates neurons during training, can help mitigate overfitting by introducing regularization. Training the network involves iteratively updating the model's weights using optimization algorithms such as stochastic gradient descent. Learning rate schedules and momentum can accelerate convergence and improve performance. Additionally, batch normalization can stabilize learning by normalizing inputs to each layer, reducing sensitivity to network initialization, and improving convergence speed. Evaluating the network's performance requires splitting data into training, validation, and test sets. The validation set is used to fine-tune hyperparameters, while the test set assesses the model's generalization ability. Metrics such as accuracy, precision, recall, and F1 score provide insights into the model's effectiveness. For imbalanced datasets, precision recall curves and area under the receiver operating characteristic curve offer a more comprehensive evaluation. In real-world applications, neural network design must accommodate constraints like computational resources and latency requirements. Edge devices, for instance, demand lightweight models that can operate efficiently with limited power and processing capabilities. Techniques like model pruning and quantization reduce model size and improve inference speed, enabling deployment on resource-constrained environments. Practical case studies demonstrate the transformative impact of neural networks across industries. In healthcare, CNNs have been employed for medical image analysis, aiding in the early detection of diseases like cancer. These models have achieved accuracy comparable to human experts, highlighting their potential to augment diagnostic processes. In finance, RNNs and LSTMs are used for stock price prediction and risk assessment, leveraging their ability to model temporal dependencies in financial data. The effectiveness of neural networks is also evident in natural language processing. Models like BERT and GPT, built on transformer architectures, have set new benchmarks in tasks such as sentiment analysis and machine translation. These models leverage attention mechanisms to capture contextual relationships within text, demonstrating the versatility of neural network architectures in handling diverse data types. In conclusion, designing neural network structures necessitates a comprehensive understanding of architecture and layers, coupled with practical implementation using frameworks like TensorFlow and PyTorch. By mastering the intricacies of neural network design, professionals can address real-world challenges and drive innovation across domains. The ongoing advancements in neural network architectures and tools promise to further enhance their capabilities, opening new avenues for AI-driven solutions in complex and dynamic environments.